Hello viewers, after a long time now I am going to start a live class. Okay, so now today we will study linear algebra. So, so this is the linear algebra and this is core 12 of your CBCS Model Syllabus. CBCS. Okay, so CBCS Model Syllabus for year class 3 or BSc all over Odisha. And this linear algebra is your fifth sem subject at core 12 and its name is linear algebra. So now I will start my lecture 1. This is from unit 1 also. So before going to linear algebra, first I will define what is a field. That means before starting your vector space, I will tell you what is field, because in every game like your cricket or football, everything you need a field. Similarly, what you will study in a linear algebra like vector space, subspace, and linear transformation, etc. Everywhere you will find a field. So if you will know what is field, then we will study linear algebra easily. Okay. So now comes to the definition of field. A non-empty set F is said to be a field. It's said to be a field if it satisfies the following properties like addition and scalar multiplication, A non-empty set F is said to be a field if it satisfies the following properties under operation. You can write the following properties under the operations addition and scalar multiplication. Okay, what are those properties? So first I will write some properties of addition. Okay, so first I can write some properties of addition. Some properties of addition. Okay, my first property will be closure property of addition. Closure property of addition. So what do we mean by closure property of addition? The closure property of addition says we can write A plus B belongs to F or all AB belongs to F. So if you will take any two element A and B from this set F, we will get their sum which also lie in F. Okay, that means for all AB belongs to F, A plus B also belongs to F. That is the closure property of addition. Similarly, what is commutative property of addition? Is the commutative property of addition. And what is commutative property? If A and B are any two elements from F, then A plus B is equal to B plus A. Okay, where AB belongs to F. So for any two element AB from F, A plus B equal to B plus A. Then third, associative property of addition. So what is associative property? Associative property of addition. So what do I mean by associative property? So if A, B, C are two elements from set F, so A plus B plus C is equal to A plus B in bracket plus C. For all A, B, C belongs to F. Sorry. For all A, B, C belongs to set F. For A, B, C belongs to set F, A plus B plus C in bracket is equal to A plus B in bracket plus C. And we know we have to first do this bracket and then we will add plus A. Then 4, after associative property, then the next property is existence of additive identity element in F. What is the existence of additive identity element? Additive identity element in F. So we know the additive identity element is 0, and here the property is saying 0 must lie in F. Okay, so we can write there exists 0 belongs to F such that A plus 0 equal to 0 plus A equal to A for all A belongs to F. So whatever the element A is, if we will add A plus 0, then this will be 0 plus A, then this will be A, and the identity element 0 must lie in F. Okay. Then the next property, existence of additive inverse element. Existence of additive inverse element in F. So we can write for all A belongs to F, there exists minus A belongs to F such that A plus minus A equal to minus A plus A equal to 0. Okay, so whatever the element A you will take, you can get minus A from F. Okay, whatever the element A you will taking from F, you will get minus A on the same set such that their addition will be 0. So these are the all properties, the properties under this operation addition. Similarly, we will take some properties from multiplication. So some properties of multiplication. First property, closure property of multiplication. This is closure property of multiplication. So like here closure property of addition, we can write A into B belongs to F for all AB belongs to F. Okay, so if A and B are any two elements from this set F, then their product must lie in the same set. That is the closure property of multiplication. Similarly, commutative property of multiplication. Commutative property of multiplication. Okay, so this is A into B is equal to B into A for all AB belongs to A. Okay, so A into B equal to B into A. Then the next property, associative property of multiplication. Associative property of multiplication. This is A into B into C in bracket is equal to A into B in bracket into C for all ABC belongs to set F. And the next property, existence of multiplicative identity element. Existence of multiplicative identity element in F. Okay, we know the multiplicative identity element is 1. Okay, and that 1 must lie in the set F. So what I can write, there exists 1 belongs to F such that A into 1 equal to 1 into A equal to A for all A belongs to F. So whatever the element A you are choosing, so A into 1 equal to 1 into A equal to A, and that element 1, which is the multiplicative identity element, that must lie in F. Okay, then next property, existence of multiplicative inverse element in F. Existence of multiplicative inverse element in set F. Okay, so for all A belongs to F, we can say this A not equal to 0. Okay, for all non-zero A belongs to F, there exists 1 by A belongs to F such that A into 1 by A equal to 1 by A into A, which will be 1. Okay, so if you will take any non-zero element A in F, there exists 1 by A in F such that their product is 1. Okay, so these are the all properties of multiplication. Similarly, we can write another property, what is that is distributive property. Okay, I can write this one as distributive property D. Okay, this is the distributive property. So distributive property says A into B plus C is equal to A into B plus A into C for all ABC belongs to set F. Okay, so there are 5 properties from addition operation and 5 properties from this operation multiplication, and 1 property from distributive, or 1 property is from distribution. Then there are 11 properties. If a non-empty set F satisfies all these 11 properties, then it is said to be a field. Okay, so I can write any non-empty set F which satisfies all the 11 properties mentioned above is said to be a field. Now we will see some examples. Okay, so we have some number field like N, Z, Q, R, and okay, I will test some number field like N, set of natural number Z, set of integer Q, set of rationals R, set of real numbers, and C, set of complex number. And we will check whether all or which of this following are filled and which are not. Okay, so if you will say for set of natural number n, that is the set of natural number, and you know set of natural number means this is from 1 2 3 4 5 like this. And if you will check whether it is a field or not, and you know it will satisfy closure property, commutative property, associative property, and when it comes to the fourth one, existence of additive identity element in F. So your additive identity element is 0. Okay, but 0 is not lying in this set S. So we can say here 0 does not belongs to the set of natural number. That means the additive identity element, 0, that is 0, is not lying in set N, is not lying in N. Okay, so the property is not satisfying, thus I can say N is not a field. Similarly, now comes to the second example, set Z, that is the set of integers. So set of integers, and what is the set of integer? This is 0 plus minus 1 plus minus 2 plus minus 3 like this. So if you will check all the 11 properties in this set of integers Z, then you will see it will satisfy all the properties of addition. That means all these 5 properties of addition. Okay, and when you will come to the properties of multiplication, okay, closure property will satisfy, you can check it. Okay, closure property will satisfy, commutative will also satisfy, associative will also satisfy, and also existence of multiplicative identity also satisfy, because the multiplicative identity element is 1 and 1 is lying in Z. Okay, and when you will come to the fifth property of this multiplication operation, then it will not satisfy. Okay, so now we'll see. So like let 5, you know 5 belongs to Z, 5 is an integer, this thing belongs to Z. So what is it? Multiplicative inverse. Its multiplicative inverse, inverse is 1 by 5, and this thing does not belongs to Z. Okay, similarly except 1 and minus 1, and for all other element you cannot find its multiplicative inverse. Like for 2, 1, its multiplicative inverse is 1 by 2, this thing does not belongs to Z. Similarly, like this 1 by 2, 1 by 3, 1 by 4, all these things are minus 1 by 2, minus 1 by 3, minus 1 by 4, all these things are not lying in Z. Okay, so since the multiplicative inverse is not lying in Z, this property is not satisfying. Similarly, we will say Z is not a field, thus Z is, or therefore Z is not a field. Simply think. Similarly, if you will come to set of rationals, this is the set of rationals, and we know the definedness of set of integers, set of rationals. This is P by Q. such that P belongs to we can say P belongs to Z and Q belongs to N, or PQ belongs to Z, Q is not equal to 0. Anything you can say P by Q such that PQ belongs to Z and Q not equal to 0. Okay, whatever it is. So this is in this form. Every element of Q is in P by Q form. Then if you will check whether all the properties are satisfying or not. So if you will see, all properties of addition will satisfy here. Okay, similarly all properties of multiplication is also satisfying here, and also distributive property is satisfying here. So since all the properties are satisfying here, we can say Q is a field. Q is a field. Similarly, if you will check for set of real number, or if you will see in the next set of complex number, all these are fields. All R and C are fields. Okay, these are all about